Okay, so that situation that I just described, where you can write a method that uses an ancestor type interface, right? So either using a class that's of an ancestor type or an interface that the classes implement, and then the method does what it's supposed to do. All of that works properly as long as everybody who's writing code remembers that in inheritance, you're supposed to follow this principle called the Liskov substitutability principle. And so this principle was described by computer scientist Dr. Barbara Liskov and her graduate student, whose name I don't remember. Click on that link, you can find out all about Dr. Liskov. She's quite famous in computing science. This principle does have a formal definition, so it does have a mathematical definition, but that's not really relevant for our purposes. It's easier to describe what this principle is supposed to do in practice in plain old English, and the idea is the following. Subclass objects must behave the same as objects of their supertype. Right? So in other words, string must behave the same way as object, at least with respect to all of the methods that object defines. So ensuring substitutability requires paying careful attention when you are overriding methods in your subclasses. If you ensure that Liskov substitutability applies, then that's what allows you to write code according to contracts of the superclass or of any interfaces that your classes implement, right? And that same code will be correct for all subclass objects, right? Even subclass objects that you don't create or that you don't know of. Right. So in other words, someone can come along and subclass one of your classes, and their new class should still work when they call a method that's written using the contracts of one of the ancestor classes. Right. So that's the idea. All right. Now the problem with this is in Java and in most object-oriented programming languages, you can simply extend a class and completely ignore this principle. Right. So for example, there's nothing from stopping you from overriding toString somewhere and throwing an exception or something like that. Right. Something that's completely unexpected at least if you look at the object version of toString. And so the responsibility of ensuring that all of this, ensuring Liskov substitutability lies with the programmer. The compiler doesn't help you at all with this. Okay, so remember, there are some ideas that we talked about when we first started talking about classes, right? We had these things called class invariants, right? We had these things called method preconditions, and we had these things called method postconditions. Right? All of these things now also apply, when you are working in inheritance. So for example, you have a superclass, right? And your superclass has some class invariants. Now remember what a class invariant is, right? It's some condition that the class promises will always be true. Right. So if your superclass has some invariants, then the invariants of the superclass apply to all of its descendant classes. Right. So if there's something your superclass promises will be true, your subclasses must also promise those things will be true. If your subclass fails to support those invariants, then any code that's written using the contracts or using the description of the methods from the superclass, that code can now fail. Okay, so here's a little example. So remember, our counter class has a class invariant, right? It says that the value of a counter is never negative. So someone can come along and write the following method, right? They're going to write a method that takes in a counter. Right? This method is going to determine, is the value of the counter even or odd? Well, it's going to determine, is it odd, right? So if it's odd, it's going to return true. If it's if it's even, it's going to return false. Right? And they write their code like this, and that would not be unusual to see from new programmers. Right? You're going to take the value of the counter, divide it by 2, and look at the remainder. If the remainder is 1, the value of the counter is odd. Right? And if it's not, then presumably the value of the counter is even. Right? You can take this code, right? That little class there. You can write every possible unit test that you can think of, right? So in other words, you can make a counter having every possible int value, right? Every possible non-negative int value, right? Pass it to this method, and this method will always this method will always return the correct value, right? So this method is provably correct, given what the counter class promises will be true. And so you should be able to take this code, hand it out to the rest of the world, right? Everybody else in the world can make some kind of counter sub-object, right? They can subclass counter, make their own kinds of counters, pass it to this method, and this method is provably correct. So it should always give you the right answer. Right? That's only true if whoever is making the subclasses remembers that Liskov substitutability they have to make sure to ensure Liskov substitutability. Okay, so someone comes along and they say, look, all of these counters are counting up. I don't want them to count up. I want them to count down instead. Furthermore, I want them to count down towards negative max value. Right. So in other words, they want a counter whose value can be negative. That breaks the class invariant of counter. So this is all going to blow up in their face. Right. So they're going to count down to integer max min value. Right. So the minimum, the most negative integer value. When it hits that value, it's going to wrap around back up to integer max value. So it's dead easy to do in Java. Right. You have your descending, you make your class, you extend counter, right. You write your constructor, right? And in your constructor, you call the superclass constructor. So that's good. Right. They've got another constructor, which also calls the superclass constructor. Everything's good. Right. Advance is now very easy to override. You just subtract one from the value. Right. And away you go. And that's it. You're done. Right. The compiler will compile it and it'll be perfectly happy with this code. Right. It's not until you make one of these objects and pass it to is odd that you might realize something's wrong. Okay. So what's wrong? The problem here is that if the value of the counter becomes negative, then in Java, when you divide it by 2 and look at the remainder is -1. It's not 1. Right? So if the sign here is negative, then the sign of the answer is also negative in Java. That's not true in all other programming languages, but in Java, that's the way it works. Right, and so now this method, so if you have a counter whose value is -1, this method says it's even, it's not odd. Right, and now that method breaks. Right, and now everybody starts to fight. Right, whoever implemented descending counter says, hey, your is odd method is broken. Right, whoever implemented is odd says, no, it's your descender counter that's the problem. It's your descending counter class that's the problem. Right. If you're assuming that Liskov substitutability should always apply, then it's the descending counter author that screwed up. Right. The fact that they let their counter go negative, right, breaks the invariant of the superclass, right, and that breaks any code that was written that assumes the class invariant was true. Right. This method works as long as the value of the counter is not negative. Right. Whoever wrote the method is allowed to assume that because the counter class has an invariant that says the value is never negative. All right, so if you have to make sure that your subclass always respects the superclass invariance, right? The question is, does that mean your subclasses have the exact same invariant? Right? And the answer is no, that's not necessarily the case. Right? So you can write a subclass, right, that inherits some class invariance, right? And that subclass can change the invariance in the subclass, right? It can change it as long as the modified invariants satisfy the inherited invariance. Right? So remember, our counter class says the value of the counter is always non-negative, and that's all that it says. Right? So someone could come along and make another kind of counter that counts up. I suppose it could count down, but anyway, counts up. Right? So they can make a range counter class, and this counter counts from some minimum value to some maximum value. Right? So instead of from 0 to integer max value, it's going to go from, say, 5 to 10 or something else that the user can pick. Right? But the minimum and maximum value are both non-negative. Right? So here, range counter extends counter. Right? You add in this case, you're going to have to add a couple of fields. You're going to have to change advance. You'll have to add some constructors. Right? But it's not easy. It's not hard to do. There's a few lines of code that you have to put in here to implement it. Right. It promises that the count will always be between min and max, will always be between min and max, where both min and max are greater than, where min is greater than 0, greater than or equal to 0, and max is greater than or equal to min. Right? So this is a different invariant than what it inherited. Right? The inherited invariant is that the value is always not negative. This invariant is different, but it also guarantees that the value is not negative. Right? So this is fine, right? At least as far as the class invariants are concerned. Right? So you can make this range counter class, and it will still behave correctly if you pass it to a method that takes in a plain old counter that assumes the value of the counter is always non-negative. So this is fine. All right, now for preconditions and postconditions, these are a little bit harder to describe. And so I'm going to cook up a new set of classes that reside in the shape hierarchy of classes. All right, if you want to see the actual implementation of these classes, you can look at the notebooks. For the substitutability notebook describes all of the classes in detail. Okay, so the idea of the, I'm going to make a set of classes that represent 2D shapes. Right? Rectangles, triangles, lines, things like that. Well, not lines, we'll see in a second, right? But basically shapes you draw on a piece of paper. Shape is going to be what's called an abstract class. Okay, so an abstract class is a class that the programmer cannot use to make objects directly. Right? So we're going to have a class called shape, but you won't be allowed to make a new shape object using the shape constructor. Right? If you try to write shape s equals new shape, the compiler will complain. Right? And because we're going to mark the class as being abstract. Do I have, yeah, right here. So here's shape, right? Now we've got this keyword abstract sitting here. Right? When you mark a class as being abstract, what you're saying is that there is no such thing as a shape object, right? Instead, what there's a bunch of subclasses of shape that have that inherit a bunch of features from this class, right? So the purpose of an abstract class is to serve as a superclass in an inheritance hierarchy. What does it do? It declares all of the methods that are common to all shapes, and it declares all of the fields that are common to all shapes. So the idea here is that you figure out what are all the common features that you want for shapes to have, and you put them in one place, right? So you put them in the shape class, right? Now, anybody who wants to make a shape object can subclass shape. Right? They can change the methods, they can add extra fields or whatever else they need to do to get a working version of their class. Right? So someone can come along and make a circle class, right? That extends shape. They get all of the stuff that shape defines, right? So they inherit everything that in all of the methods and fields from shape, and then they can complete their class. So the purpose of an abstract class is to serve as a building block for other classes. If you're going to draw this in a UML class diagram, it looks exactly the same as a regular shape, as a regular class, except the name is written in italics, right? And so that's what indicates this is abstract. Okay, so what are we going to have, or what features are going to be common to all shapes? Well, every shape is going to have a width. Every shape is going to have a height. Right? Notice that they're protected, so the subclasses can see these fields. Right? The class is a bit funny, right? So it says that all shapes shall have a width and height that are between 1 and 100 units. Right? So there's a minimum length and a maximum length for all shapes, right? 1 to 100. There might be some constructors and so on and so on and so forth. Right? So an abstract class is allowed to have constructors. The constructors will probably set width and height, right? The constructors can even be public, but if you try to use one directly, so if you try to write new shape, the compiler will complain, again, because the class is abstract, right? You're not supposed to make plain old shape objects. Okay, so we have a width method. So width, not surprisingly, is just going to return that field there, right? And it has a description up here, right? It promises it returns the width of the shape and that the return value shall always be between 1 and 100, right? Which makes sense if you look at the invariance for the class, right? The class says all shapes have a size between 1 and 100. Okay, area upper bound. So here's another method. So this method says it returns an upper bound on the area of the shape. So you can imagine that some shapes will have an area that's very hard to calculate. So if you have a shape that's got some squiggly perimeter, maybe it's got a hole or holes in it, right? It's very hard to calculate the area of that shape exactly. Instead of computing the exact area, the shape class computes an upper bound on the area, right? So in other words, it computes some value for the area that is greater than or equal to the true area, right? And it's easy to do if you have the width and height of the box that encloses the shape, right? It's just the width times the height. So that's just the rectangle that encloses the shape. Now, obviously, if you have a class like circle where you can compute the exact area of the shape, the circle class should go ahead and compute the exact area in this method, right? And so that's what this part's trying to say, right? The method simply returns the value equal to the width times the height. Subclasses should override the method if they can provide a better upper bound. Right? So something like circle, return pi r squared, where r is either the width or the height, right? Something like rectangle would just return width times height. And so on and so on and so forth. Right? Triangle would return 1/2 the width times the height, right? And that would be the exact area of the triangle. Okay, and finally we have set dimensions. So set dimensions here, if you look at the code very quickly, you can see it's going to have a couple of preconditions. So set dimensions changes the width and the height of the shape to the specified width and height, right? So if you pass in 1 and 10, you get a new shape whose size is 1 and 10. It validates the inputs, right? So make sure width and height are between 1 and 100, right? And if it's not, it throws an exception, right? So in other words, set dimensions ensures that the class invariants are respected. Otherwise, it simply sets the width to width, the height to height. All right, so now you've got this shape class. We don't have any shape objects yet, right? So we don't have rectangle, we don't have circle, we don't have triangle, right? But you can now start writing code using the shape class. Right. So for example, I can write a method that randomly changes the size of any shape, right? So in other words, it randomly changes the width and height of the shape. The code here looks a little bit funny. So what this is going to do, so 0.01 is 1%, right? Everybody agrees on that? So 1 minus 0.0, sorry. So 0.1 is 1%. So I'm going to multiply 0.1 by math.random. Right? Math.random returns a value between 0 and 1. Right? And then I'm going to subtract 0.5%. Right? So what that value is here, right? That value is always between negative 0.5% and 0.5%. Right? I'm going to add that to 1, which is 100%. Right? So the width is going to get scaled by 99 point. So the new width will become somewhere between 99.5% or 100.5% of the original width, right? So this randomly scales the width by some small amount. It does the exact same thing with the height, right? Now, if the width of your shape is already 1, or if the height of your shape is already 100, then randomly changing those values might cause them to go out of range, right? So before we call set dimensions, we're going to make sure that the new width and height are inside the range 1 and 100, right? If they are, go ahead and call set dimensions. We know that that's not going to throw an exception because we're passing in a value between 1 and 100. You can cook up whatever shape you want, pass it to this method. This method will always do the correct thing, right? It will always randomly change the width and height of the shape by some small amount if it can. And if it can't, it leaves the dimensions of the shape unchanged. Right? So that's fine. Right? Okay. Now, someone comes along, right? And they make a class called rectangle. Right? And I guess someone else comes along and makes a class called square. So rectangle extends shape, and someone makes a class square that extends rectangle. Right? This is exactly the same as the circle ellipse issue. Right? Just imagine this is ellipse, imagine that circle, right? You look at that and you should immediately think something funny is going to happen here, right? The square, yeah, it's a rectangle, but it's a rectangle where the width and height are exactly the same. So something funny is going to happen here. Now remember, set dimensions, it has some preconditions, right? It requires that the width and height be between 1 and 100, right? If a method has preconditions, if a superclass method has preconditions and the subclass decides to override that method, right, then the subclass must accept all the parameter values that are accepted by its ancestor class, right? So shape says all values between 1 and 100 are valid, right, for both the width and the height. What that means is that for all other subclasses, the values 1 to 100 must also be acceptable for the width and height when you call set dimensions, right? You can't say, okay, the width and height must be between 20 and 30, right, in a subclass, right? That breaks, that imposes an extra condition that set dimensions doesn't have. All right, so square is going to be one of these classes that's going to try to do this. So whoever implements square is going to override set dimensions so that it throws an exception if the width and height are not equal, right? So someone comes along and says, hey, I'm going to make square, right? I can't use the set dimensions, or I don't want the set dimensions method that I inherited from shape, right? Because that set dimensions method always changes the width and height, and perhaps to different values. And I no longer have a square, right? So they impose an extra constraint. Right? If the width is not equal to the height, we're going to throw an exception, right? So they've added an extra precondition here, right? And this precondition, right, is not compatible with the superclass precondition back here, right? The precondition from the ancestor class says that any value of width and height is legal as long as they're between 1 and 100. Square is now saying any value of width and height between 1 and 100 is legal as long as the width and height are both the same, right? Okay, so after that precondition is checked, they're going to change the dimensions of the shape, right? So in other words, they're going to set this width and this height. You could write this dot width equals width and this dot height equals height here, right? But remember, you've already got a set dimensions method defined in a superclass somewhere, right? So can you call that already defined method, right? Can you call the method that we're currently overriding, right? And the answer is yes, right? I can call the superclass version of set dimensions using the keyword super, right? So there's the second use of the keyword super, right? Inside of a constructor, it calls the superclass constructor. Inside of a method, it calls the superclass version of the method. Okay. Now what happens when you pass a square to random scale? Right? So you pass a square object here. The method computes a random width and height. Almost certainly they're not going to be the same. Right? You get past the if statement. Right? So assume that the new width and height are between 1 and 100, but they're not equal. And now you call set dimensions. Right? Which version of set dimensions gets called? Well, if you passed in a square, right, it's the square version of set dimensions that gets called. And now the square version of set dimensions throws an exception. Right? So a method which was once provably correct, or is actually not once, which is provably correct, suddenly fails, which is a contradiction. That doesn't seem to make any sense. Right? Why does it fail? It's because whoever implemented square forgot about Liskov substitutability. Right? Their square class is actually not substitutable for shape, right? Because they imposed an extra precondition on this method. All right, so, oops. Oh, here's an aside. Okay, so notice that when you override a method, it's often the case that your method, when you override a method, you're going to do some extra stuff that the superclass method doesn't do. But then you want to do everything that the superclass method does do, right? And so if that's the situation you're in, then you can always call the overridden version of the method, right? You can call the superclass version of the method, right? So in square, right, I'm using the super keyword to call set dimensions. Now, when you use this keyword, you call what ends up happening is you call the immediate superclass version of the method, right? So this calls the rectangle version of set dimensions, right? if the rectangle version of set dimensions does not override the shape version, then you get the shape version of set dimensions. Right? If it does override it, then you get the rectangle version of set dimensions. So if you want to call the superclass method in the method that you're overriding, just use the keyword super in front, right? And that will let you call the superclass version of the method. Don't use this, right? Don't write this dot set dimensions, right? If you write this dot set dimensions, you call that version of set dimensions again, and this method becomes infinitely recursive. Right? If you want to call the superclass version, oops, sorry, make sure to use the superclass keyword here, the super keyword here. All right, so if you are overriding a method that has preconditions, right, you are allowed to change the preconditions. Right? What you can't do is you cannot add extra preconditions, right, or you can't strengthen the constraints on the parameter values. Right? So, for example, in set dimensions, you can't say that the width must be between 10 and 30. Right? That strengthens the constraints, right? It used to be between 1 and 100. Now you're saying it's between 10 and 30. That's no good, right? If you do that, anybody that's, if you call some method that assumes that the value of the width and height can be between 1 and 100, that method's not going to break, right? But you can remove the preconditions that you inherited, right? Or you can weaken the constraints on the parameter values, right? So in set dimensions, you can say something like, I'm going to accept any value between 0 and 100. That's fine, right? And in particular, so we're going to implement rectangle so that it overrides set dimensions. Right? It will accept any value for the width and height, and it's just going to fix the value if it's out of range. Right? Instead of throwing an exception, right? It's just going to say, okay, so this is less than 1, I'm going to make it 1, or it's greater than 100, I'm going to make it 100. Right? And so we're going to remove the precondition now. Right? Notice here, right? There's no precondition anymore. Right? So we removed the precondition that we inherited. This is fine as long as we make sure that all the class invariants are still true. Right? Up here, we even say what we're going to do if you give me an invalid width or height. Right? We're simply going to all values less than 1 will get set to 1. All values bigger than 100 will get set to 100. Right? There's the code that will do it. You could write some if statements here if you wanted to. Right? It turns out it's easier to use max in this case. So math.max returns the maximum of these two values. So for the width, I'm going to make sure that the width is the larger value of the width or the min or 1. Right? So if width is less than 1, width gets set to 1. We're going to do the same thing for the height. Right? So if you want to make sure that a value is at least equal to some value, use max. Right? If you want to make sure that a value is no bigger than some value, use min. Right? So here we're going to take the min of width and 100 in this case. Right? If width is bigger than 100, we're going to set width to 100. And then go ahead and set width and height. Right? Now there's no exception thrown. There's no precondition on the method. Everything's fine. Right? Any value that's accepted by the shape version of set dimensions for the width or height is also accepted by this version of the method. Right? Furthermore, this method makes sure that makes sure to not set the width or height to be out of range for shape. Right? So this is fine. So you can remove or weaken precondition. You can remove constraints or weaken constraints on your parameters in a subclass method. Okay. So the preconditions don't have to be exactly the same. All right, so that's invariance and preconditions. Finally, we've got postconditions. So if your method returns a value, then you have to make, and you decide to override that method, you have to make sure that when you override the method, whatever value you return has to satisfy whatever the superclass version of the method said it would do. Right? So the width, and there's a height method as well in shape. Right? They promise to always return a value between 1 and 100. Right? So they're making something. They're making a promise on the returned value of the method. Okay, so we're going to write a little method here. I think this slide has. Have I changed? Is this the updated version? Sorry, just let me quickly check. Okay. Oh no, this is not the updated version. Oh no, it is. It's right here. Okay. I should have, at some point, I have to fix this so that it's a better example. All right, so we're going to write a method here that scales the size of a shape uniformly, right? So in other words, it's going to change the size of the shape, but it's not going to change the aspect ratio of the shape, right? So it's going to scale it uniformly up or down. Sorry, down in this case, so that the width of the shape becomes equal to 1. Right? So if we have a shape whose width is 50, right, we're going to scale it down by a factor. We're going to try to scale it down by a factor of 50. Right? So in other words, we're going to take the height divided by 50, we're going to take the width divided by 50, and that'll be its new width and height. Right? So whenever you're doing something to a value to fit it between 0 and 1, we say that you're trying to normalize you're trying to normalize that quantity. Right? And it turns out that normalizing quantities is used a lot. So you, for example, you can normalize the height. You can't normalize the area of a shape in this case. That won't work because it'll end up setting the one of the two dimensions to less than 1, probably. Right. Now we've got this funny constraint on our shape class, right? The shape class says your dimensions will always be between 1 and 100. So if I'm going to divide the height by the width, I have to make sure that the height is greater than the width. Right? If it's not, when I take the height and divide it by the width, I get a value that's less than 1, and that breaks the class invariant. Right? So there is this precondition here that the height must be greater than the width. Right? So there should be a comment up here that says that the height is greater than the width, right? As that should be your precondition. Right? Assuming that precondition holds, you can go ahead and write this method. Take the height divided by the width just becomes 1, and now call set dimensions. Right? So this works for every shape that you can imagine, as long as the height of the shape is bigger than the width. Right? That will always work. All right, so someone comes along and they cook up a class called vertical line. Right? So a vertical line, the programmer decides, shall have a width of 0. Right? Which is bad in 2 cases. Right? So number 1 is going to break a class invariant. Right? The width is supposed to be at least 1. Right? And furthermore, it's now going to break the post condition of width, the method width. Right? Width says it always returns a value between 1 and 100. Now we're going to return 0. Right? Again, this is easy to do. Right? You simply extend shape. Right? You've got access to the width field in shape, so you can set width to 0. That's a problem. Right? You've broken the invariant, right, that you inherited from shape. Right? And now you override width so that it always returns 0. Right? And now that also breaks the post condition that you inherited from the superclass version of width. Right? What's the problem? Right? Now when you call normalize width, that method fails as soon as you pass it a vertical line object. Right? So now you call normalize width, you pass in a vertical line. Right? Remember, its width is 0. So what version of width and height? Which version of the height method do you get when you call height, and which version of the width method do you get when you call width? Right? You get the vertical line version of the method. Well, that takes its height and divides it by 0, which produces a height of infinity, right? So positive double dot positive infinity, right? You then set the width to 1, or this method then sets the width to 1, which now screws up the vertical line class, right? Because the vertical line class says its width is always 1. And then you call set dimensions, and now the infinite height causes an exception to be thrown. So a method that was once correct, or is correct technically, right, is no longer correct when you pass it a vertical line object. Right? So that's no good either. What happened, whoever extended shape by creating vertical line did some things they're not supposed to do. Right? They broke a class invariant. They broke a post condition on a method that was inherited from the superclass. Now, if your method promises to return something, if a superclass method promises to return something, the subclass doesn't have to return the exact same value. Right? The value that it returns must simply satisfy whatever the superclass version of the method says it's going to do. Right? So if you make a triangle class, we can override area upper bound to return the exact area of the triangle. Right? Again, doing this is very easy to do, right? You make a new class that extends shape. You add your constructors, right? Area upper bound, you override it. Instead of returning the width times the height, you return 1/2 the width times the height. That's the area of a triangle, right? So remember, the inherited version of this method says that it's an upper bound on the area, right? The triangle version of the method says it returns the true area, right? The true area is still an upper bound on the actual area, right? It just happens to be also equal to its actual area. So this is fine, right? You can change the value that a method returns as long as the post condition that you inherited is still true, right? Is this an upper bound on the area? Yes, this is still an upper bound on the area. Everything's fine. Okay, so what happens if you have a method that changes the state of an object, right? So if a method changes the state of an object, that changes the state of the object part is one of the post conditions of the method, right? So if you've got a method that promises to change the state of an object in some way, and you decide to override it, right, then your overridden version of the method must also change the state of the object in a similar way, right? Okay, so back to square. So we know square is already broken, right? Because its set dimensions method's busted. So whoever created square decides they're going to quote unquote fix their version of set dimensions, right? It's no longer going to impose the constraint, right? So they said, oh, look, I added this extra constraint. I'm not supposed to do that, so I'm going to remove that, right? So here, instead of throwing an exception if the width and height are not the same, they're just going to ignore the height, right? So they're going to call the superclass version of set dimensions passing in the width and width, right? Which is good for square. The square is still a square, right? But it breaks the promise from the superclass version of set dimensions, right? Set dimensions promised it's going to change the width to that, and it's going to change the height to that, right? Now, when you get a square, or when you get when you have a method that takes in a square object that calls set dimensions, right? Suddenly, this value is no longer used. Right? So what happens here, right? So if imagine someone writes a method that takes in a shape, right? Their method calls set dimensions so that the shape always fits inside of another shape, right? Now you pass that method a square. The square version of set dimensions ignores the height, right? So now when you pass that method a square, that square might not fit into the shape that you're trying to fit it inside of, right? And it's because whoever implemented square decided to ignore the height parameter, the value for height. Okay, so again, someone complains to whoever created square, right? And so the implementer of squares decides they're going to again try to fix their method, right? This time, they're going to say set dimensions does nothing, right? And they're going to tell everybody, hey, look, don't use set dimensions if you've got a square, use set length instead, right? So set length only takes in one parameter, right? And it sets the dimensions of the square to length and length, right? But now you've got a problem down here, right? So the fact that you're doing nothing, right, means, again, you've broken the promise that the superclass version of the method said it would do, right? The shape version of set dimension says the width of the new shape shall be width, or sorry, the width of the shape will be changed to that. The height of the shape will be changed to that, right? And now this does nothing. So again, you write a method that takes in a shape that fits the shape inside of something else, right? That method is going to call set dimensions. You pass it a square. The size of the square never changes. It never fits into your other shape, right? There's no way to fix the square class in this case. Right? So there's no way to make square extend rectangle in this. There's no way to make square extend shape either, right? In this particular hierarchy of classes. If you really want a square as one of your shapes, you have to go in and change the superclass. Right? So you have to go in and change the shape class to say that set dimensions does something else or may do something else. All right. And so that concludes, I think, the discussion of inheritance for this year. All right. So that's it for today's lecture. I guess I'll see you again next week. Remember,